All right, so in the last class, we started talking about PLC hardware, and I showed you this picture of a basic PLC and some of the major sections. We just kind of did an overview, and the major sections are the power supply. Every PLC will have a power supply. In this section over here, input-output sections. There's two pieces of that. There's input modules and output modules, and then you have they use the term controller here. Sometimes they'll just call that the CPU, but that controller houses the CPU. And then this one actually has a communications module. Not all PLCs have that, but every PLC will have a power supply, CPU, input-output modules, and a place for you to put in the program. And so in the last class, we kind of did an overview of the PLC hardware and how you would use it and to replace hardwire switches or relay contacts. And then what we want to do today, and we'll do the same thing on Friday, we'll kind of drill down deeper into each of these subsections of the PLC. So the very first thing I want to talk about is the input-output section of the PLC. So I have this PowerPoint I want to share with you. And then this first picture I showed you in the other PowerPoint from last class, you pretty much want to just kind of commit this to memory. So these are the major portions of the PLC. I showed you the picture so you kind of have a reference, but you have your input module, or input modules. You have your output modules, and those are the places you connect your switches or sensors if you're trying to sense an input signal or whatever it is you're controlling. You can connect that directly to the output module, and if the output module can't provide enough current, sometimes you have a relay that you connect to the output module and have the relay control whatever load you're switching off and on. It might be a motor or some kind of large load. Of course, every PLC will have a power supply. And then this device down here, the programming device, well, that's the way you get the program into and out of the CPU. And once the program is in the CPU, then you can disconnect the programming device, let the PLC run. You never have to connect that back to the PLC unit unless you want to edit the program or completely change the program. Typically, the programming device has its own memory, its own RAM. And so when you enter in the program, you're entering in the program to the programming device, and then usually there's some kind of step to where you have to transfer the logic, your program, from the programming device to the CPU. And there's a download button or enter button, some kind of way you'll be able to transfer the code from the programming device to the CPU. So this PowerPoint talks about the I/O section, input-output section, and basically the way to think about this is for any sense you have on your body, the sense of sight, sense of touch, smell, whatever sense you have on your body, we have electronic or electrical sensors that can perform that same kind of function. And so we have sensors that we can sense temperature, we can sense the presence of absence of something. We have sensors that can actually taste, and I'm doing air quotes that you can't really see. So we have sensors that can do a multitude of things that we can connect to the input of the PLC. And then in addition to that, we have a variety of switches and buttons that we can connect to the PLC. And so we'll talk about some of those as we go through the class. And this refers us to the picture of the PLC. So some of these terms here, I'll just kind of go back to I'll mention these terms. I'll go back to the picture in just a second. I'll kind of point out so you kind of have a point of reference of what we're talking about. So it says the I/O section consists of a rack and modules. And then you have two types of modules. You have input modules and you have output modules. Of course, input modules accept signals coming in, and output modules put out certain signals depending on the results of how you write your program. So you have these modules. So the term here on this slide, important term, this idea of a rack. The rack is just a place you plug the modules into. Sometimes they call it a chassis. Some can call it a chassis or a rack. And then this term slot. Well, if you remember that we mentioned that the PLC, most PLCs, the larger ones, they are modular. So you can get a really small PLC. I say as small as just a little larger than a pack of cigarettes, and that's a unit where you have the power supply, the input, the output connectors all in one unit. But once you go above those small micro PLCs, then you get into the type of PLCs where you have these components or these modules or pieces. So each of these sections you can pull out. And over here we focus on the input output section. I can take this module right here and actually pull that out. And the whole chassis, they refer to as a rack. But when you pull the module out, that space that's left behind, that's a slot. And there's a little plug on the back of that, the module called a backplane, and you can just kind of snap that module back to the backplane, and you can plug different types of modules into a slot. So pretty much any slot can take practically any kind of module for a specific family or line of PLCs. So this, again, is just to give you a reference point, and you can kind of refer to this diagram. As I said, when we're face-to-face, typically I would bring in the PLC. We take it apart in front of the class, talk about each part. I do that one time at the beginning of the class, and that way you kind of have a point of reference so that when I'm going through these PowerPoints, you kind of know what I'm talking about. But here you can just refer to the picture. So I'm going to switch back to the PowerPoint. Here is this is a 128 I/O rack. The 128 is the number of connection points you have. You have connection points. So there's a couple things I want to point out here. So notice that I have these modules. There's 8 of them. But notice that when we count, we started the count with 0 right here. So we go 0 through 7. That's 8. So when we deal with digital, we don't start our count with 1. We start count with 0. And that's always the case. So you'll see that when we talk about bit positions, or we talk about naming or numbering a row of a truth table, or a input-output module, we always start our count with 0. So 0 through 7, there's 8 modules here, and each module will have, for this particular setup, each module will have 16 connection points where I can connect a switch, or I can connect some kind of device I want to control. So that's where the 128 comes from. If you take 8 divided into 128, you'll get the 16 that I'm referring to. Now the size of this ends up being important, but I don't want to get into that now. We'll get into that later, because the size of this basically determines the size of certain things that's going to exist in memory, called registers, which I've already mentioned. But again, I'll come back to that. So this is a physical rack. This is a physical rack. This is hardware. Remember in the last class we talked about virtual devices? Virtual devices. So we have real-world devices. The main ones used with PLCs, so the most common one is, of course, a relay, either a control or a logic relay. But then there's also timers and counters. You can actually have relays and timers and counters. You can have those. You can have a PLC mimic those in memory. And when we mimic a relay or timer or counter in memory, we call that a virtual device or logical device. Well, it turns out we can do the same thing with a whole PLC rack. We have a physical rack that is the actual PLC I/O section that you can touch and you can interact with. But then there's something called a logical rack. A logical rack. So I want to talk about a logical rack, and this turns out to be pretty important because you actually have to interact with this logical rack. So let me go away from the PowerPoint, and I want to show you oh, you know what? I might not have uploaded that. Give me 1 second, guys. I think I might have forgot to upload something that I need. So give me. Hopefully, I'm going to switch off of my collaborating. Hopefully, it doesn't cause the system to crash. Sometimes when I do this, it causes the system to crash. But we'll see what happens. Okay, I don't think I crashed the system, so that's good. Let me upload this file. Let's see. Okay, there. I already had it uploaded. All right. All right. Anyway, sorry about that. So a logical rack. So this diagram is important. So let me attempt to explain this. So I want you to think of, first of all, we have two sections. We have the top section, they call this a output image table, and the bottom section is an input image table. And they use the word image because it's an image of, you can think of it as an image, a virtual image of the input modules and a virtual image of the output modules. So think of it as a snapshot in memory of something that physically exists. And the way to think about this is, well, first of all, notice that for my output image table, I have this, these are the addresses here. And so it begins with the O for output, and down here for my input image table, it begins with the I for input. Now, this is part of what we call addressing, which turns out to be important, and we'll get to that in another slide. But so basically, this first column right here is a list of all the output modules. So for every one of these rows, there's a physical output module that this is kind of a reflection of. And remember I said earlier that when we start to count or we number things in digital, we always start with 0 instead of 1. Normally as humans, we go 1, 2, 3, 4. We start our count with 1. Computers always start their count with 0. So in this addressing schema, what you have here is you have this first part of the address, which is an O, so that's an output, we'll call it a row for now. And down here, I is an input. But then after that, you have these numbers. So we start our count with 0, we go 0, 1, 2, 3, 4, 5, all the way down to 7. So these numbers here represent the 7, and I got to account for 0, so the 8 represents the 8 cards that we have that are output cards. Now when you think about the rows, I want you to think of these rows as, think of them as cells. So you got these cells, these boxes. It's hard for me to draw on this whiteboard. Think of these as cells like this. And each of these numbers right here stands for one of the cells. So the 0th cell is like right here. Cell number 1 is like right here. Cell number 2 is right here, and so forth. Now you might notice something about this numbering system. If you look at it, we start counting at 0. We count from 0 through 7. We skip 8, 9, and we go right up to 10, 11, 12, 13, 14, all the way up to 17. So we'll talk about this in a later class, probably next week whenever we talk about number systems. But what this is a special type of a number system called Octo. If you look at the very bottom down here in small print, it says Allen Bradley PLCs use the Octo numbering system. So Octo numbering system is a numbering system based on base 8. So I don't want you to focus on that right now, because again, we'll deal with that in another lecture. We'll deal with numbering systems, and you'll understand Octo. But for now, just think of these as slots. Each of these slots, and each one of these slots is numbered. So what I can do is I can uniquely locate a slot, and all I need is 2 pieces of information. Say I want to locate this slot right here. So that is in row 2 of an output module, and these numbers right here actually represent bit positions. And so the slots that I asked you to imagine these numbers represent slots. What you would put in those slots is a 1 or a 0. So actually this input image table or output image table is kind of a map of where my 1s and 0s are. Okay, so for every, let me go back to the PowerPoint. For every, let me find the slide. All right, so for every connection point on this diagram, let's say that this is an input module. So this is an input module, and this particular input module, there are going to be 16 connection points. So there's actually 16 physical screw terminals that you can unscrew and connect a switch or a button to. There's 16. And if you connect a switch or a button to one of those 16 connection points, that switch or button can either be open or closed. Well, the point of the image table in memory, it tells you that each one of those terminal screws that you can connect to is mapped to one of these bit positions in this table right here. So it's kind of hard to think about, but I mean, really, it's not that hard to think about. Basically, for every screw terminal, every connection point, there's a place in memory that uniquely maps to that. And what you store in that position in memory is a 0 or 1, and that 0 or 1 is a reflection of whether the switch connected to that particular screw terminal that's mapped to that particular cell, whether that switch is open or closed. So let me jump down to the input image table since we're talking about switches. If I had a physical switch connected to maybe connected to input card number 1, which is this one, this screw terminal label number 2, which is that one. Well, whatever switch is connected to that, if that switch is open in bit position number 2 of input card 1, if that switch is open, then in that slot, in that cell, there will be stored a 0. If that switch is closed, then in that cell and that slot will be stored a 1. If that switch opens and closes, then the bit value in this particular slot will change in accordance of whether that switch is open or closed. And so what PLCs do, and I don't want to get ahead of myself, but they're constantly watching whether a switch is open or closed, but not the physical switches. The CPU is actually monitoring this input image table to see if it's looking for the presence or absence of a 1. If it sees a 1 at a particular bit location, then it knows that the switch mapped to that is closed. If it sees a 0 in that particular bit location, then it knows the switch mapped to that particular bit position is open. And the way it works is you'll write a program, and based on whether there's a 0 or 1 or the switch is open or closed, you can have an output happen or not happen. So that's kind of how this works in a kind of a big way. Now, I don't expect you to completely understand what I just said, but this input image table comes up again, and I'll keep mentioning this. Let me just say this though, that I don't know if you guys have downloaded your software. You can download the free version of it, but when we actually do the labs, you need to get the full-blown version. But in your actual software, they have these tables. They don't refer to them as input image tables or output image tables. That's a textbook thing. In the real world, with real working PLCs, they call it input image table or output image table. They call those data tables. So a data table is equal to an image table. But we'll get to that again too. We get closer to using the actual program. So I'll refer back to this logical rack often, and you'll get more and more familiar with it. So I want to go back to the PowerPoint now. All right, so some terms here. A logical rack is a virtual addressable unit, and all that means is virtual means it's not a physical thing you can hold in your hand. It only exists in memory. Remember, you can have virtual relays, you can have virtual counters, you can have virtual timers. It's just a software device. It's a program. It exists in memory. It says it's a virtual addressable unit, which means that you can read, you can write to it, and you can read from it. I can put a 0 or 1 at a certain spot, and I can look to see if there's a 0 or 1 at a certain spot. If I'm putting a 0 or 1 there, we call that a write. If I'm looking to see if there's a presence of 0 or 1 in the table, then we call that a read. So you can actually read and write to this data table or image table. The next term is, well, we'll get to words later on. So I've already mentioned the fact that in textbooks, they usually use the term image table, output image table, input image table, but you actually call it a data table. So you probably never, I mean, I'll refer to it as an image table, but you actually, when you interact with your software, you'll always think of it as a data table. It's the same thing. So they talk about I/O groups. That's not a big thing. What the I/O group is that, I'll just mention it quickly. All the I/O group is well, let me show you. When you think of these rows for the output and the inputs, it's kind of corresponding to each other. So like if I pick this one right here, I pick this right here. The address is the output module, and it's output module 01. Well, you can pair that down here with the input module, and that's that same number 01. So they call that an I/O pair. Now that's not really that important, but you might see that term, and if you see that term, that's what they're referring to. So I'm going to go back to the PowerPoint. I think that's all I really want to say about this. This slide right here, I don't know if you, I think I showed you a way to print your PowerPoints so you can have 3 slides to a page and the note pages on the side. If you actually did that, well, here's one of those places I want you to mark this slide, because I'll ask you about this slide on a quiz or exam. So this shows that you can actually take racks and you can connect them together, much like you can connect computers together. So a single computer by itself is good. If I can have that computer talk to another one, we call that networking computers, and that's even better because I can share resources. Well, I can do exactly the same thing with these racks. These racks, each one, I can have the rack actually can be a whole nother PLC, or it can just be the I/O section part of the PLC. But whatever I have, the reason for doing this, for networking these together, or for having a remote rack, is because when you do it, you can minimize the wiring. Instead of running all the wires to the main PLC, you can actually have the rack part of it out. Let's say that maybe you have a control room, and then you have a factory where your manufacturing process is taking place. You can actually have the rack, the physical rack, located closer to where the switches and sensors are, and then you can run just a couple lines to the actual PLC, and then that greatly reduces the wiring. And so just digging into this slide a little bit more, when you have a remote rack or a remote PLC, I can have just the rack connected remotely, or another PLC that talks to a PLC. Pretty much anything you can do with a computer, you can do with a PLC, because a PLC is a computer. So this thing I have circled can be just the I/O section that you move closer to the manufacturing process, or it can be a whole nother PLC that this main PLC over here on the left is talking to. But however you decide to set the system or network up, you got to have a way of having the local PC talk to the remote rack, or the local PLC talk to the remote PLC. So you got to have some kind of communication medium. And there's mainly 3 communication medium that we use with PLCs. The 2 most common is coaxial cable and fiber cable, or fiber optic cable. I'm sure you've heard of both of those. So coaxial cable is like if you have your cable TV, you know, they have a cable line that comes in, and you can, if you were to unscrew that cable line and remove the connector, you'll see a copper braid with a center conductor. That's coaxial cable. You've all seen that before. It has the black coating around it. You may or may not have seen fiber optic cable, but fiber optic cable is made out of either really thin glass or really thin plastic. And the difference is if you have a coaxial cable, copper, then you actually use electrical current to send data back and forth from the main PLC to the rack. If you use fiber cable, a fiber optic cable, you don't use electricity. Fiber cable transmits light, so it changes the bits and bytes to pulses of light and sends the pulses of light to the machine back and forth. And if you have fiber optics, you've probably heard of Cincinnati Bell fiber optics, or Phi optics, I think they call it Phi optics. All that is basically fiber optic systems. They get away from electricity and they send information back and forth using pulses of light. You might wonder why they do that. Well, there are certain advantages to fiber, but there's also disadvantages. So I want to talk about those. So the main advantage to coaxial cable is, number one, compared to fiber optic cable, is really inexpensive. Coaxial cable compared to fiber is really inexpensive. The other advantage to coaxial cable is, let's say you have to run a lot of this coax throughout your factory or your process. Well, anytime you have to bend to go around something, so you have to make a sharp 90-degree turn, you can do that really, really easy with coax. You cannot do that with fiber. If you try to put a 90-degree bend or turn in a piece of fiber, then it'll break. So fiber is much harder to work with compared to coaxial cable. So the advantage of coaxial cable is that it's inexpensive and it's very flexible, but the disadvantage is it has a limited range. So for this, the range is 2 miles. And you might think, well, 2 miles, that's a lot of cable. But if you're actually running hundreds or even, in some cases, thousands of wires throughout a really big factory, 2 miles is really not all that much. So advantage of coaxial cable: coax, inexpensive, and it's flexible, it's easy to work with. Where fiber is expensive and it's harder to work with. If you have to make a sharp turn, you can't just bend the fiber. You have to actually splice it, and then you have to reconnect it a certain way. And there's a certain level of skill required to connecting 2 pieces of fiber together. You can't just twist them together and solder them like you can do cable or wire cable. With fiber optic cable, you have to have a certain level of skill, and you have to have certain special equipment to take 2 fibers and connect them together correctly. So you will want to know here, the takeaway is, know why we use remote racks or remote PLCs, why we would network racks or PLCs. The reason we do that is to reduce or minimize wiring. And you want to know the mediums. The main medium is coaxial cable or fiber. I said there were 3 because the one that I didn't talk about is, of course, wireless. nowadays, many devices are wireless. Matter of fact, Bluetooth, when you use your Bluetooth devices, Bluetooth is actually a wireless protocol. So your earphones or whatever wireless you have controlling devices in your house, that Bluetooth is actual a protocol or set of rules that we agree on when we're designing wireless devices to talk to each other. So wireless is another one that I don't have here. Specifically, I want you to understand fiber and coax and know the advantage and disadvantage of each of those. All right. So it mentions here that each remote rack has requires a unique station number. So let me get into addressing a little bit. Now, I mentioned to you in another class that a PLC and the computer are basically the same device. The difference is a PLC is designed to work in an industrial environment. So it's going to be sealed so it can't pick up dust. It's going to have circuitry to control the temperature. It's going to be what I call, it's going to be, you can think of it as a heavy-duty computer, designed to work where there's a lot of dirt, grime, temperature variations, whatever kind of environmental hazard you might subject this thing to, is designed to handle it. Well, there's another big difference that we'll kind of get into as the weeks go, but I'll say it now. When you have a regular computer, a PC, or even for this fact, your cell phone, even those kind of devices, the smallest piece of data that you can address is a set of 8 bits together, ones and zeros in groups of 8. Now we're going to give that a name. I'll tell you, it's called a byte, but typically when we represent, for a regular PC, we represent any kind of information. What I mean by that is a letter from the alphabet, a number, a sound, a pixel of a picture or piece of a video. It's all represented using 8 bytes or 8 bits, which is called a byte. So the smallest piece of information you can address is 8 bits on a regular PC or other digital devices like your cell phone. Well, here's where PLCs were different. With the PLC, you can actually address individual bits. And we'll talk about the importance of that as we go along. So that's one big thing to know. Well, if we're going to address a bit, then how do I actually get down to the bit level? And that's the idea of addressing. So addressing is, how do I find if I have hundreds or thousands of bits in this grid, or this input-output image table, how do I get to the exact one I want to store or read the 1 and 0 to or from? How do I do that? And how do I map those screw terminals that I have a switch or sensor connected to? How do I map that screw terminal to a particular cell? That's all addressing. And so I'll just say a little bit about it right now. So a basic address, there's no standard address. The address schema is going to depend on who makes the PLC. All manufacturers have different addressing schemas. And for some, like Allen Bradley, depending on which model PLC you use or you buy, one may have one in that family of Allen Bradley. They may have several different address schemas. So this one is kind of, I'm going to show you in just a second. It's based on a particular Allen Bradley PLC family. But basically, the address will give you this information. It'll tell you what type of module or slot you have. There's going to be an input module or output module. So just by looking at the address, you should be able to tell what kind of module is this. And then which slot is it plugged in? And then when you find the slot that is plugged in, which screw terminal, or if I'm thinking about the input-output image table, which actual cell or slot am I putting the 0 or 1 in? So the address kind of goes from a real wide to kind of points to one specific location, kind of like a map, a regular map. If I tell you what state you're in, and then from the state, what city, and then from the city, what neighborhood, and then from the neighborhood, what street, and then from the street, every house has a house address, and we can even say what room you're in. That's what I mean by address. You kind of go from the real wide to the narrow. we got to be able to do that with bits, ones and zeros in the PLC. So kind of an example of that is this. Now this one is the address format for this particular PLC, Allen Bradley PLC 5. This is the addressing format for that. And this was close to the one you'll use in your simulation software. It's just a little different, but once you understand one of them, you understand all of them. So the very first part of this address is you're either going to have an O there or an I. If it's an O, we know we're talking about an output module. If it's an I, we're talking about an input module. But think about in memory, that input or output image table, if there's an O, then the virtual structure I'm looking at is going to be an output image table. If it's an I, the virtual logical structure I'm looking at is an input image table. So the very first part of this, the leftmost, tells you, am I dealing with an output module or an input module? And then this one, in this particular addressing schema for PLC 5, they have a file number, So each PLC will have a file number and then a rack number. And then over here, the most important part is that rack number. A rack, think of a rack as one of those modules that's equivalent to a row of that grid that I showed you of the input and output image table. So once you know what row or what rack we're dealing with, then you figure out, all right, which screw terminal am I connected to, and that's the actual bit address. So if I was connected to, remember they count with 0, 0, 1, 2. If I was connected to maybe terminal 2, the third one from the beginning, starting with 0, 1, terminal 2, then this bit address here would say 0, 2. So I can go from the Y down to a specific bit location, and either physically, if I'm talking about a physical output module, or if I'm looking in memory, I can figure out specifically which cell that 0 or 1 is stored in. And so addressing becomes important. I don't care too much about this. This is just when you deal with I/O modules, a point card is just, a point is the number of connection points you have. So I can have one with 8 terminals, screw terminals you can connect 8 switches to. So they call it an 8-point card. So typically when you buy these, you can have a 8-point card, a 16-point card, a 32-point card, and they actually make them smaller than 8, although I don't know, when you get smaller than 8, I don't know if you actually would call that a PLC. You probably call it a microcontroller. I don't know if you actually call it a PLC. About this, I don't have anything to say about the points on the card. So that's a point. I do have another one, but let me pause for a second because I've been doing a lot of talking. Anybody have any questions over anything I've talked about in regards to this PowerPoint on input-output modules? Any questions or comments?
So are there multiple types of addressing formats?
Wait a minute, hold on a second. I don't know what it is with my audio here. Let me see if I can turn it up. Okay, ask me that again.
Okay, so are there multiple types of addressing formats?
Yeah,
this is just like an example.
Yeah, so the address, well, they're all going to work the same way. Where think of the example I gave you of a map where you have we tell you what country you're in, and then what state, and then what city, and then what town, what street, what house, the house number, and then the room number. They're all going to work that way, but the way they show that might differ. And yeah, they're different depending on if you look at for instance Allen Bradley, the one I just showed you, the PLC 5. The one the simulation software you're going to use is based on the Allen Bradley. They call it SLC 500, SLC 500. So it's pretty close to this. It's going to be a little bit different. But if you get one from Siemens, their format will be completely different. It'll work the same way where it goes from a wide to a small, but once you kind of understand any of the PLC addressing formats. The learning curve to any other manufacturer, once you understand one, you'll understand them all. They'll be just a little different. One might use a colon, another might use a semicolon or a dash for something. It's that kind of thing. But they're all pretty much the same way. Once you learn to drive a car, pretty much you can drive any car. It's kind of like that. But all cars are different. Any other questions? Okay, well, let me go to this. Let's see how am I doing on time. I had to move to a different room because turns out another professor had a lab, and I keep getting kicked around from room to room. And so I have to make sure things are, and I don't have a clock in this one, so I got to use the one on the computer. But let me go to the other PowerPoint. We'll get through that. And I'm running out of time, so I'm going to go through it kind of quickly. But I'll be happy to stay around after class if anybody has any questions if I go too fast. So this next one deals with the CPU. And CPU, that stands for Central Processing Unit. The Central Processing Unit. And this next slide is important. So again, if you printed out your PowerPoints as note pages and 3 note pages to a page, and you have the notes on the side, here's another one of those you want to mark. You want to mark this one. You want to make sure you understand that the main sections of the CPU that we concern ourselves with is a processor, and the processor is sometimes called a microprocessor. So it's a microprocessor, there's memory, and then there's power. The CPU has to be powered. And notice the direction of arrows. So for the power supply, that power supply is powering that microprocessor. That energy flow or arrow flow is one way, but notice that when that processor talks to memory, it goes 2 ways. So the processor can put something into memory, we call that a write. The processor can take something out of memory, we call that a read. And what it's going to put in or take out of memory, of course, are 1s and 0s. At the very bottom, there's a little note here. It says, strictly speaking, the microprocessor is not the same as the CPU. Strictly speaking, the CPU contains the microprocessor. Nowadays, I'm not so sure that that's, you can probably, it's safe to call the microprocessor the CPU. I think nowadays it's safe to think of them as the same unit. So mark this slide if you have your PowerPoints printed out. Now, this next one, every PLC will have some kind of switch or button or lever like this one. So you have these different modes. So you have, and this will be a little confusing at first because here's what happens. You program the PLC. That's not like a computer. When you interact with the keyboard on the computer or your cell phone or some device like that, when you interact with the keyboard on the computer, those 1s and 0s, as soon as you press a key, go right into the computer, the microprocessor, and the memory, goes right into the CPU. Well, with a PLC, the programming device has its own memory. So what you do is you write your program, and it stays in the keyboard or the handheld device. There's several ways you can program a PLC, and we'll talk about a couple different ways. But that program is going to stay in the programming device until you move it from the programming device to the actual PLC. Well, when you do that, I think on your simulation software, they call it downloading it. There's an actual button. You'll make the program, and you'll click this button that says download. And then when you download, you're moving your program to the actual memory of the CPU. And then if you want to run it, you got to tell the PLC, hey, I'm not editing this anymore. I want to actually run it. So the 2 important positions are the program position and the run position. So if you're actually programming your PLC, you'll have this switch or knob or lever. You'll have that in program mode. So you'll have it set right here. Once you get the program set, there'll be some kind of button or something for you to press or click to move that program from the programming device to the actual PLC. And once that's done, at that point, if you want to, you can disconnect the programming device. You don't need it anymore. However, you got to make sure that you change this switch or whatever mechanism they have. You have to change that from program over to run. Now you'll see this when you use your simulation software. It'll be second nature to it. You'll make a few mistakes. You'll write your program and then you'll try to run it, and you'll say, hey, I can't run it because you haven't downloaded it yet. So this will become crystal clear when you actually work with your software. So the main two important modes here, the run mode and the program mode. And as I said, you'll become quite familiar with those. There's a remote. They have these different remotes. So not all PLCs will have a run mode and a program mode, but not all PLCs will have this remote. So the remote mode, you can have a remote run, remote edit, remote test. You can do you can do these operations. You don't have to be right in front of the PLC when you do it. We're not going to concern ourselves with that with the remote mode. You want to remember the run mode and the program mode. What does the CPU do? Well, here are the main, these are the main functions of the CPU. So it executes the operating system. Well, what is an operating system? Let me click off of this for a second. I don't want to run out of time. Let me just click off and go to the camera. So think of something that you're familiar with, like your cell phone or your computer. So you are the user. So this is you. That's the user. And you want to interact with what you call an app on your cell phone. So you got apps on your cell phone. Well, Word, Excel, those things are all app. App is short for application. So you got this app you wanna interact with. So maybe it's Microsoft Word. So that app actually, you can cause physical things to happen with the computer or whatever it is you're using. For instance, in Microsoft Word, there's a place you can go up to, and you can click the icon of a printer, and that click physically causes the printer to engage and to print out a document. So you want to interact with hardware. Well, what happens is you don't interact directly. This application does not interact directly with the hardware. There's a layer of programs in between called the OS, and the OS stands for operating system. In a PC, you know some operating system. There's Windows. Windows is an operating system. You may have heard of Linux or Unix. Those are operating systems. On your cell phone, you know, Apple, I don't know what Apple OS, and then I don't have a cell phone, but you guys know if you have a Google phone, they have operating systems. So that's the layer of software. Think of it as a program. It's really not one program. It's really a layer of programs. But for purposes of this class, think of it as a program. And the operating system is the part that it interacts between the application software and the actual physical hardware. This is my hardware. So this is my printer. Whatever thing you can touch that program has control over, then we call that hardware. So the OS actually interacts with the hardware. So on this PowerPoint, let me go back to it. We talk about what does the CPU do? Well, part of it is it interacts with the operating system, the OS. Memory management has to do with a lot of things, but basically putting ones and zeros. It can be kind of misleading because we like to think of those rows and columns in that table I told you about, and we like to think that that data is always put in a certain order and they're all the ones, but that might not necessarily be the case. So memory management can be kind of complicated to talk about, but it controls memory. The CPU has to monitor inputs. Now, it doesn't actually monitor inputs directly. What it does is it looks at the input image table, and that's how it monitors the inputs. Remember what the input image table is. It's a reflection of a logical or virtual reflection of all those screw terminals that you have switches connected to. And so for every physical screw terminal that you can connect a switch or a wire to, there's a software location with a specific address that can hold a 1 or a 0. And you can map that screw terminal to that cell using an address. And once you do that, the state of that switch being open or closed will cause the presence of a 1 or 0 to be in that particular cell that it's mapped to. And that's what the CPU is looking at. It's really looking at the input image table to see where the 1s and 0s are and how they're changing. Evaluates the ladder. Now, ladder is, for lack of a better word, it's just a program that you write. It's called a ladder, or the correct term is ladder logic. They refer to it as ladder logic because when you write the program, when you're done and you stand back and look at it, it looks like the ladder that you climb on to paint a house. It looks like a ladder. So they call it ladder logic. And then it turns on appropriate output. So depending on when that CPU, when it looks at your input image table to see if the switches are open or closed, if there's 1s or 0s in certain locations of the input image table, and then it's going to look at the program that you wrote, and depending on what you tell it to do with those 1s and 0s, either it's going to have an output come on or go off. And whatever's connected to that particular output, it will physically turn that output on or off, thereby controlling that machine. So controls appropriate outputs. Now, I only got a couple minutes, but this slide right here is really, really, really important. So what I might do, let me see how many slides I got. Yeah, I can get through this. So these terms here, I'm going to go over a little, guys. So I'm just going to keep going, probably about 5 minutes over. If you got to sign off, do that. When I put this on YouTube, make sure you go back and watch the back part of this lecture. Mark this slide. Now, this is probably the most important slide that we've talked about today. These terms right here, I want to make sure you're familiar with these terms. We'll use these terms, well, most of these terms, for the rest of the semester. So the first one is a bit. We already talked about bits. A bit is short for binary digit. A bit is a 0 or 1. The term byte is a group of bits. Byte refers to 8 bits. So a byte is equal to 8 bits. A kilobyte. Now, this is where you can run into trouble, so please listen. And again, if you got to sign off, come back and hear what I'm going to say. You can have if you look at the slide here, you can have a K with a capital B and a K with a lowercase b. It can be confusing. So if you have a K with a capital B, that's a kilobyte. A K with a lowercase b, that's a kilobit. So you don't really see kilobits much nowadays, but back a long time ago, probably before you guys were born, you didn't just get up and get on the internet. What you had to do was you had to use a dial-in service, America Online or some kind of dial-in service, and use this modem. We actually dial a phone number, and you hang the modem up, hang your telephone into this modem, or it would connect to the computer. And that modem, when it transferred the digital information, it was serial data transfer, and you know what that means now. Serial data transfer means that those bits were transferred bit by bit by bit, kind of in series or single file. In those days, the internet was super slow because we use those modems that use serial data transfer. So it would take, I'm doing air quotes, it would take all day to move your web page from your computer or your information from one computer to another. In those days, they measured the speed of the modem in kilobits. How many bits per second can we move? Because we're moving these bits one by one, so that's important. Well, you don't really have that nowadays, so that term kilobit is kind of being phased out. But to talk about it, most of the time we refer to kilobytes. But here's the difference. If it's a kilobyte, you know, because you guys are engineering students, you know kilo means 1,000, but it only means 1,000 if we're talking bits. A kilobit is 1,000 bits. A kilobyte, because we're dealing with a number system called binary, a kilobyte, my light just went out. A kilobyte is 1,024 bytes. So write that down somewhere, that a kilobyte is not 1,000 bytes, it's 1024, it's 1,024 bytes. Now that's important because One of the things you'll have to do for me is calculate the size of memory. If I want the size of memory in bits, the calculation is going to look one way. If I want the size of memory in bytes, it's going to look another way. Most of the time, we're interested in the memory size in bytes. How many bytes and how many bytes of memory do you have? Now, the only reason we bring up bits is because unlike a computer, a PC, or a cell phone, it deals with bytes. You can move 8 bits at a time. It deals with bytes, so kilobytes is important. But the PLC can actually address and manipulate individual bits. That's why you got to understand kilobits. So if it's a kilobit, you're going to multiply by 1,000. If it's a kilobyte, you're going to multiply by 1,024. So you want to remember that. I'm going to skip over the other two and go right to the bottom. This term volatile and non-volatile, that's important. It refers to, basically it refers to memory. So if I have memory that's volatile, well, let me do non-volatile first. So if I have memory that's non-volatile, then it'll retain whatever's in it, regardless of whether there's power or not. If it's volatile, when power is removed, whatever is in the memory is erased. Example of that is this. If you, let's say you're typing a document using Word on a PC and you haven't saved it yet. Well, you haven't saved it yet. Where is that document in memory? Where does it live? Where does it exist? The answer is it exists in something called RAM, R-A-M, RAM. RAM stands for Random Access Memory. We'll get into the details of that a number of times, but it's in RAM, and RAM happens to be volatile. So if you haven't saved your document yet and you're typing it, it's in RAM. If your little brother comes and trips on the computer and pulls the cord out, turns it off, your whole document is lost because RAM is volatile. Now, if you save it, you're actually saving it, and let's say you have a solid state drive. If you save it, that solid state drive, you can think of it as really storage, but you can think of it as memory. It's non-volatile. It's going to hold that 0 or 1 whether there's power or not. So if you had it saved, then when you tripped over the cord, you can turn it back on, and your information is still there. So the term volatile and non-volatile is kind of important. So that doesn't make sense. You guys can ask me about that later. Let me jump down to the last 2 slides. I'm already over. This right here, I think, kind of, hopefully this clears up what I was trying to say. So here I have an input module. I got this input module. I'm only showing so each one of these squares right here, there'll be like a screw terminal right here and here. Now these screw terminals. And if you count over here, I think I got 1, 2, 3, 4. There's probably 16 of these spaces, these slots in the input image table. And so this switch right here, this closed switch, this blue arrow is showing that it's mapped to this bit position. And since that switch is closed, in that bit position in the input image table, there's a 1 stored. If this opened up, this would change to a 0. Now here I have this open switch. This green line shows it's mapped to this bit position. You map it using the address, but notice that this switch is open. The contact is open. So in that bit position mapped to this switch, there's going to be a 0 stored there. And it's the same thing with the output image table. Now the output image table, the 1 and 0 in the output image table, whether there's a 1 in a particular bit position or a 0, depends on the program you write. It's going to look at the logic that you write in that ladder diagram I referred to, and it's going to look at the 1s and 0s in the input image table. And depending on the outcome of that logic, you're either going to have a 1 in the particular bit position of the output module, or you're going to have a 0 in that bit position. If there's a 1 in that bit position, like there is right here, if there's a 1, then whatever's mapped to that screw terminal on the output module is going to turn that device on. If there's a 0, whatever's mapped to that particular bit position is going to turn it off. So I know I went through that kind of quickly. I apologize for that. I'll be more than happy to stick around after class to if I need to go back over anything, or if you think of more questions, then when we get together on Friday, I'll be happy to go back to this and we can talk about anything you want to talk about for these two PowerPoints. So let me ask real quick, anybody have any questions or comments before we sign off? Okay, well then guys, have a great rest of the day. I'll see you on Friday. If between now and then you think of something, write it down, and when we come online on camera on Friday, you can ask about it. And if not, we'll just keep plowing right along and get through this stuff. And I think number systems is next week, so I think you'll be really interested in that. Have a great rest of the day, and I'll see you later.